Hello guys, today we are going to treat the subject of spreading of influence, namely SI as it's used in the literature, in social networks or graphs. You can see that the spreading of influence in any situation nowadays. So just imagine how the spreading of the coronavirus has happened. In this scenario, the whole world is modeled as a vast social network where nodes are people and edges between them are relationship that represent friendships, for instance. In other words, I, as a node and as a person, have a certain probability of infecting my friends and spreading the virus. A lot of biology and epidemiology researchers have tried to model the spreading of diseases through mathematical processes, and they came up with various solutions, which we're going to talk about in this lecture. In the end, I am going to provide you with a broader framework that generalizes some models and can be exploited to generate your custom-made SI model. This lesson is divided into two parts, a theoretical part and a practical part. The theoretical part gives you all the building blocks to implement these models on your own, and this time we are going to do the practical part in Python instead of Java to show you how easy can the described models be used. Without further ado, let's get to it. This slide enlists the models that we are going to talk about in increasing order of complexity. So the first one is the most simple one, which has different very simple and abstract assumptions, whereas the last one is the most complete one and the most complex one. The last model is a generalization of the linear threshold model and the independent cascade model. It can be used to devise new spreading of influence strategies, which are ad hoc for your application. Generally, spreading of influence models have an underlying weighted directed graph structure. Nodes transit through influential states such as susceptible, infected, recovered, or active or non-active states. Let's now talk about the SIR, so the susceptible, infected, and recovered model. You can find more information in the link enlisted below. The SRI model is instrumental in biology and virology, so it has been broadly studied by virologists. You can assume that the underlying graph is that of the spread of the coronavirus in these months. As the name suggests, SIR has three different node states. When the node is in the susceptible state, it can get infected by its infected neighbors. Infected nodes can recover just as COVID-19 patients have been doing in these last months. Finally, recovered patients become immune and do not get the virus again, which doesn't always represent reality. For instance, seasonal flu also infects those people that were infected last season. You can read more about the SRR model in the link in the slide as I mentioned before. More formally, the infection procedure of the SIR has different waves denoted as time steps, which we use the letter T to denote. At each time step T, only those nodes infected in the previous time, so previous time step T minus 1, can infect its neighbors with a specific probability beta. At the end of the time step T, the infected nodes in the previous wave get recovered. Now we are going to see a caveat in the practical part where the recovery rate, so the recovery rate of each node can be represented as a probability. Here we assume that the recovery rate has a probability of 100%. So at the end of each wave, every node that has been infected in the previous wave will be recovered. Let us see a dummy example. So here we have 7 nodes connected according to the graph structure in this picture, and we assume that the infection probability for each node is equal to 1/2. So we have 50% of infecting each vertex in our one-hop outgoing neighborhood. Let's assume that we begin with a single infected node, which is node 5. Okay, so at time step T equal 1, node 5 has 50% of probability to infect its neighbors 3 and 6. It only succeeds at infecting node 3 and not 6, so 3 becomes a red node, so an infected node. Recall that at the end of each time step, the nodes infected in the previous step get recovered. Therefore, 5 recovers and cannot be infected anymore. Now, 3 can only influence vertex 1 and assume that it succeeds. At the end of time step T2, 3 will get recovered. Now, vertex 1 has 2 neighbors, right? So, and it infects both. So we assume that it can infect both. And 4 becomes infected at the end of this time step. So 1 and 4, 2 and 4 become infected. And at the end of this time step, no 1 will recover. So it will become a green node. Okay, now because we have 2 infected nodes, we need to know which one to visit first. So we need to know which one from 2 and 4 will infect first. Here we assume that the adjacency list of each node is ordered in increasing order. So it's node 2's turn to infect. Node 2 cannot infect node 4 anymore since it's already infected. So it tries to infect vertex 7 and succeeds. Now it's the turn of node 4. Because 4 doesn't have any outgoing connections, its infection procedure halts without further infections. At the end of this time step, both 2 and 4 recover. Now node 7 has to try and infect more nodes in the graph. But because node 7 has only incoming links, node 7 recovers and the spreading of influence according to the SIR model halts. The next type of SI model, so spreading of influence model, is that of the tipping model, or also known as the deterministic threshold model. The tipping model is associated with a seed and target set of nodes. It is strictly related to the maximum influence problem, which, given an initial set of active nodes, one has to maximize the final set of infective nodes. So we want a bigger set at the end of this procedure. So this is what the maximum influence problem entails. In the tipping model, there are 2 different states, an active state and an inactive state. And each node transitions from an inactive to an active state if a portion theta of its incoming neighbors are active. For more details, check the link in this slide. Okay, let's give you some notation so you can understand what's going on. Assume that you have an underlying graph G with a set of vertices V and a set of weighted directed edges E. We do not need weights here, still they can be used to extend the vanilla model. We define the incoming and the outgoing neighborhoods of each node indexed with I. So n sub I, ind, is the set of incoming neighbors of node V sub I. We also define the size of these sets with the letter D and its corresponding sub and subscript. Recall that the node gets active if a portion theta of its incoming neighbors is already active. We can define this function theta for each node V sub I and then use this to model the infection. Hence, theta of V sub I returns a real number in the interval 0, 1 with both extremes included, which determines the susceptibility for a node to get infected. By exploiting theta, we can calculate the necessary number of neighboring nodes that need to infect V sub I. We label this number with K sub I. So K sub I is the actual number that the incoming neighbors of a certain node V sub I have to be in order to get V sub I infected. Okay. Now, for the spreading of influence to work, we need to define how the nodes get activated in a monotonically non-decreasing fashion. Hence, having the threshold function, we can define an activation function A sub theta that, given a subset of vertices, returns another subset of vertices, V prime, such that its nodes satisfy the condition in the slides here. For a node v sub I to be put in the resulting subset, so the subset that this activation function a sub theta v prime produces, the length of the intersection between its incoming neighbors, so n sub I ind, and v prime and the infected nodes in the previous step has to be greater than or equal to k sub I. So if this condition is satisfied, then v sub I is going to be in this produced set. Okay, in order to perform a spreading of influence model, we need to apply the activation function iteratively to obtain a maximally influenced set of nodes at the end of the algorithm. Thus, the algorithm converges when the activation function of the current time step and that of the previous one produce the same output set of newly activated nodes. So when this condition is met. I'm going to show you this process in the following slides, and at most you can get as many steps as there are nodes in the graph G. But this is very, very uncommon, so you are not going to execute all the steps. Alright, so this is an example. Suppose that we have the same graph structure as in the previous example with the SIR model. Suppose for the model the threshold function is equal to 50% for each node in the graph, so theta is equal to 0.5. And finally, the initial set v prime is 1 and 2. You can view the v prime set as the initial set of active nodes. So at the beginning of the first wave, t equal 1, only 1 and 2 are newly activated. We distinguish the new from the old activated nodes for illustration purposes. But remember that the tipping model has only two states, active and inactive. When a node transitions to an active state, it cannot go back to an inactive one. Now, because theta is 50%, each node gets infected if at least half of its incoming neighbors are active. Keep that in mind because it's going to emerge in the next slide. Okay, let us see how the incoming neighborhood is formed for each node in the previous graph. K sub I represents the size of the incoming neighborhoods. So n sub I ind, the row here represents the incoming neighborhood for node 1, which is only node 3, and node 2, which is the set containing only node 1. For node 3, it's the set of containing node 1, 5, and 6, and so on. 5 doesn't have any incoming neighbors, and so on and so forth. So K sub I instead represents the cardinality, so the length of the set of the incoming neighbors for each node. So in this case is 1, in this case is also 1, in this case is 3, so here's my mistake, so it should be 3. Okay, in this case is 3, in this case is also 3, in this case is 2. Right, so okay, and alright, now we grab this table and we show the activation function condition. Now the first row of the table shows the intersection between the currently active nodes and the incoming nodes for each vertex. The second row tells us if the size of the intersection is greater than or equal to the portion of neighbors k sub I for a node to become active. Therefore, the activation for the first time step t equal 1 is the union of v prime and the set that corresponds to the nodes that have a true value in the second column. So basically here, because theta is 0.5, so we only need 50% of our incoming neighbors to be active for us to become active, and these are the conditions that are met. Basically because this condition here is satisfied. So the condition that we stated in this slide, and we only grab those nodes, so the nodes corresponding to the labels, to the true Boolean labels. So the set of produced nodes is 2, 4, 5, and 7. 1 shouldn't be here. Okay, so this is my bad, but 1 shouldn't be here. So it's only 2, 4, 5, and 7, and the union between 1 and 2, 1 and 2 is this set here. Now let us move on. Notice how different shades of red discriminate between new and old influence nodes. Again, notice that the procedure described previously could be optimized by not considering the nodes already in V prime. So therefore the previous table would only contain 5 columns instead of 7. So 1 and 2 shouldn't be here, could also be omitted because they are already present in V prime. Okay, so the newly infected nodes are those in bright red, and those in darker red are the old infected nodes. Let's begin with the second wave. The threshold remains the same throughout the whole execution, but V prime changes to the result of the activation function. So this set here now becomes a new V prime set. Again, we use the same table as before and determine the intersections and whether its length exceeds k sub I. Vertex 6 added in the newly formed set is added in the newly formed set, thus producing the entire set V of nodes in the graph, because there's a true Boolean value here, and you have this new set that satisfies the condition, and the union of both these sets consist of the whole set of the nodes. So therefore it is unnecessary to proceed with another iteration, since we have fully maximized our influence problem, because we already cover the whole set of nodes in graph G. And the bright red nodes become dark nodes, and the algorithm finishes its execution. In general, we can say that the algorithm has converged because of the converging criterion that we have stated in the previous slide. So the slide here, which states this one, if the output of the activation function with the threshold theta at time t is equal to the output of the activation function with threshold theta in time t minus 1. If these sets are equal, then the process converges, and we have this convergence here. Okay, now we pass to more complex models. The independent cascade, from now on we refer to it as IC, has two states as in the previous model. The IC model is a generalization of the SIR model, where the probability beta of infecting a neighbor can be randomly chosen for each pair of nodes V sub I, j. Now, V sub I, j represents an edge in the graph going from node I to node j. And as I said, this is a generalized SIR model, and beta is randomly chosen. As usual, when a node is active, it cannot transit to an inactive state. So this is a constraint for this model. Here, the IC model starts with a set of initially active nodes, key sub 0. For any inactive node V sub I, each of its neighbors tries to activate it. I'm going to explain the activation criteria in the following slides. The convergence criterion is similar to that of the tipping model. The currently active node set is equal to the previous active node set, so this is the same criterion as in the previous one, but here we have currently activated nodes and previously activated nodes, and we don't have an activation function depending on theta, but you can rewrite the independent cascade using the notation of the tipping model, or vice versa. Okay, each node V sub I has a probability P sub I, j to infect its outgoing neighbor v sub j. Now imagine these probabilities as weights of a social network. We are not going to illustrate an example because it's very similar to the tipping model, with the only change that the probability of activating the nodes doesn't depend on the number of its active neighbors, instead on a specific probability for each edge. So this is the specific probability p sub I comma j, which is the beta for the pair of nodes v sub I comma j. Okay. Lastly, in the linear threshold model, each node v sub I chooses a threshold theta v sub I from a uniform distribution. The underlying distribution which to choose from isn't important, so you can also select different distribution, but the authors in this reference here choose a uniform distribution. Okay, at each time step t, a node gets activated if the sum of the edge weights, so the probabilities, of its incoming active neighbors exceeds its threshold. So the LT model generalizes the tipping model, where the condition in the activation function changes with that in the formula presented here. Now notice that this model works only under the constraint that the weights of the incoming edges at a particular node v sub I sum up to 1. So this is the condition that a node, let me just wait until this menu disappears. Okay, this is the condition where the node, a node Vj, gets activated if the sum of probabilities of its incoming active nodes, so this Vj in n sub I ind intersection key sub t minus 1 means get all the incoming neighbors that have already been active in the previous time step. Get their probabilities, sum their probabilities, and check whether the sum of those probabilities is greater than or equal to the theta, so the threshold of node v sub j. If that's the case, then v sub j transits from an inactive node state to an active node state. Okay, now we're not going to show an example here because we are going to implement this on our own just to see the underlying mechanism of the linear threshold model. Now finally, we can, once we draw the threshold for each node in the real numbers interval from 0 and 1 with the extremes included, the LT model generalizes a tipping model. So the activation function, the condition of the activation function can be rewritten by replacing the condition of the tipping model with that we specified in the previous slide. Now, finally, the most general model is the generalized threshold. Now, you can have the generalized threshold model and the general cascade model. Now, the general threshold model is a broader framework for the linear threshold model, whereas the general cascade model, which we're not going to treat here, you can go to the reference 2 and see how the authors have generalized these two models. But basically, given a node v sub I and a monotone function f sub v and a threshold function, so a threshold value for each node v sub I in the interval of real numbers of the set of real numbers from 0 to 1, and an active set of nodes key sub t at time t, v sub I is infected at time step t if the monotone function applied to the active set at time t exceeds a certain threshold. So now the monotone function can be anything, because you don't need to have it stated as a union of sets. It can be anything, but the output of that monotone function f sub v should be bounded in 0 and 1 because we're talking about probabilities. So if the value is bound from 0 to 1 and the threshold is bound from 0 to 1, if that value produced exceeds the threshold, then we put the node vi in the active set of nodes key sub t. Now the condition is left unchanged as seen previously, but now instead of the activation function, as I mentioned before, we use this function that we created, f sub v. Now this concludes the theoretical part, and let us now get our hands dirty with code. We are going to implement the SIR model, the linear threshold model, IC, so the independent cascade model, and the tipping model. We are not going to implement the general threshold model because it's application dependent, and you can use it if you have a certain scenario in which you need a general threshold model and you don't want to rely on pre-built and vanilla models. Now we are going to rely on pre-implemented solution using the ndlib library for the independent cascade and the tipping model, whereas we are going to use the EON, so EON package for SIR. Finally, as I mentioned before, we will implement the linear threshold model by ourselves to understand how its underlying mechanics work. Now this is what we are going to do, and I have already installed the necessary packages. So the first package that you're going to install is pip install eon. We are going to use Python 3.7, I think. Let me just check in a minute which version. 3.7.4, because it's the most supported version of Python, since Python 2.6 has been deprecated at the beginning of this year. Okay, now you need to, I'm using Linux, so I am assuming that if you use Windows, you can install these packages on your own, but I'm going to give links on where to get the installations. As a matter of fact, I'm just going to epidemics. I'm just going to show you the links where you can epidemics on networks.readthedocs.io and latest. So this is latest. So this is the EON package, and then ndlib. You just go on Google, and this is the documentation for ndlib. So these are the two things that we're going to use: EON for SIR and ndlib for independent cascade and the tipping model. Okay, now you can use pip install eon in order to install the package for Python. I already did that, so it's already satisfied. And if you want to, the cool thing about eon is that it permits you to animate the process of infection and recovery states between the nodes in a certain graph, right? And in order to animate this thing into a GIF or an MP4, you can use fmpeg. So I think that I have fmpeg. Install ffmpeg. Okay, so I need to be root, obviously. Install fmpeg. I think there's a similar tool for Windows. Okay, I have already ffmpeg. This is a tongue twister. Yeah, I already have this package installed, so you can install this in order to animate the graph that we are going to use, for example, that we are going to use, and to see how the nodes transit from one state to another. Okay, so now SIR provides an SIR algorithm in different flavors. Now we're going only to use fast SIR because that's a simulation for exponentially distributed infections and recovery times. And notice that this particular model in EON you need to specify the maximum number of iterations to execute the SIR model. We in the theoretical part, we assume that we went on to infect every other node, so we didn't specify maximum threshold. But in reality, because graphs can be very large, then you need to determine how many iterations are you going to do. Now you can also leave it blank, so you can, if by leaving blank, then the library gets that you want to execute the SIR model until there are no more models to be infected, so you basically maximizing the influence problem. Or if you want to specify a cutoff by the maximum number of iterations. Now, a strange thing here is that we've used a different notation in theory, and then Eon uses a completely different notation. But don't worry. Now, I'm going to before going to the implementation, I'm going to basically anticipate you what the notation of Eon is for SIR model. Now, tau, the Greek letter tau in Eon represents the beta probability. Now, we've used beta, they use tau. Rho, the Greek letter rho, is the fraction of initially infected nodes. So basically, this thing here. Now, fraction of infected nodes is how specifies how many nodes are initially infected. In this case, we had 1/7. So our rho was 1/7, and suppose that 1/7 got us with 5 initially infected, node 5 initially infected. Okay, and then gamma represents the recovery rate, which I have anticipated you. So in theory we use gamma as 1, so the probability that an infected node recovered, we used 1. So at the end of each time step, each infected node gets recovered, so with 100% of probability. Instead, you can specify it to be lower than 1, and then you can see how the recovery rate impacts the infection procedure. Okay, so let us go and change on desktop. I'm going to use Visual Studio Code, but you can use any other IDE or even the interactive Python shell. But now I'm going to use this IDE, create a new file, save that file in desktop, and we say SIR model. I'm going to name it as SIR_model.py. Okay, so basically the things that we need, this is going to be very short because it's a short and simple model. Now I'm going to use network X to create my graphs, because I don't want to create them manually, so I'm going to use network X, and then I'm just going to import Eon as Eon, yeah. And I want to create 50 nodes, so this is the number of nodes for the graph. And there's a cool feature of network X that lets you create graphs on the fly, so graphs with a known structure. Now if you have a different application, then you must create your own graph, but for illustration purposes we're going to use pre-structured graphs, and we are basically going to use here the Barabasi-Albert graph, which means that each node where you specify a parameter, let's say m, and then this particular structure, this Barabasi-Albert graph says that each node is going to be connected to exactly m nodes, and this is quite interesting. Albert graph, we say n, so we give it 50 nodes, and we say, okay, we need to connect it to each node is going to get connected to 5 nodes. So each node is connected to exactly 5 nodes. Okay, so then we say T max. We want to have at maximum 20 iterations, so 20 iterations at max. And then we say tau, which was the beta probability, which is, let's say, 0.3. Now this is the transmission probability as specified in the documentation of EON. If you go to EON and then see the SRI model, you will have these kinds of notations. So the beta probability is going to be called tau, and it's going to be denominated as the transmission probability. Okay, gamma, which was our recovery rate, let's say 0.8, so recovery rate. Let's see what happens. And rho, which is the number of initially infected, the percentage of initially infected nodes, we say that it's 40%, so percentage of initially infected rows. Yeah, let us now see this SRR model. So eon.fast SIR, give it the graph G, tau, gamma, rho, to specify rho, because we do this because rho is an optional parameter, so we need to say what rho is. So if you go to the documentation, the rho also there was named as rho, so we could also here name it as x, and we say x, but we maintain a consistent notation. And then T max is T max. Notice that if you don't specify T max, so if you say none, this algorithm will go indefinitely until convergence, so until there are many other nodes to get infected. T max is T max, and return full data. This is just a cool feature to say, okay, return everything that you have had in all the iterations. So I don't want only the final output of the infected nodes, but I want every infection for each iteration. And then I can animate this model, because I want to see how using FFmpeg to see how this how the infection procedure goes on. Okay, and then I'm just going to save it as, I don't know, SIR model Tmax equal 20.mp4. Okay, now I'm just going to execute it. Python SIR model, no model name, network X. Okay, so pip install network. Network. It's not network X. It should be network X. So now, okay, network X. It should go well. Hopefully, was deprecated and will be removed. Use MP iterable. Yeah, just warnings about the versions. Let us see how it goes. Okay, it has converged, so it has finished all its iterations, and now you can play your MP4 or your GIF, and you can see the green nodes are in a susceptible state, the red nodes are infected, and the gray nodes are recovered. And as time goes on, the infected nodes will get to 0, and the recovered nodes will get to the number of nodes. Now let us see it again. Obviously, the number of susceptible nodes will go down with time, because they will get either infected or either recovered. Now this is a cool simulation in the Barabasi-Albert graph, where each node was connected to five different nodes. Now if we change the gamma to 1, let us see what happens. We would expect that the recovery nodes will be increased even earlier than the previous one, because you have a recovery rate of 100%. Now let us see. Okay, let us see here. Yeah, the recovery nodes are recovering. have been recovered at the iterations also before the fourth iteration. See, now this here, the x-axis represents the iterations, whereas the y-axis represents the number of nodes. Okay, so this is the SIR model. Now let us move to the tipping model, and the tipping model is basically implemented in the ndlib package in Python. You can look for the documentation, you can find it easily, but let us move with a new file. So let us create a new file, let us save it, desktop, and say tipping model.py. Also here we are going to implement the network X as an X library, no, as an X. Okay, then import ndlib.models.modelConfig as MC. So this basically configurates the model with the initial state of the model, and the core part here, ndlib.models.epidemics threshold model as TM. Okay, so this is the main thing that we're going to use. Let us now use another structure for the graph, and we are going to use an Erdős-Renyi graph, which basically, given a probability, states that each node is connected to another node, to all the other nodes with a certain probability. We shall use here a probability of 5%, so we have a very sparse graph. So Erdős-Renyi graph, say that we want 1,000 of nodes, and we have a probability to be connected to each other node of 5%, so we have a completely sparse graph. Okay, so now here recall that the model, the threshold model works as follows. Each node has its own threshold. During a generic iteration, every node is observed if and only if a node is infected, if and only if the percentage of its infected neighbors, so incoming neighbors, is greater than its threshold. So if it's greater than its threshold, then the node becomes infected. Okay, now let us let us create the model. So tm.threshold model g. Okay, let us configure the model. So mc.modelconfig, configuration. Sorry, configuration. Okay, and let us say that only 10% of the initial nodes are infected. So let's say config.add model parameter percentage infected 0.1. Okay, so this is the percentage of him. This percentage, here's a typo. Okay, so 10% of initial nodes are infected. Okay, now let us see the threshold. Although you can specify different thresholds for each node, I'm going to choose 0.15 threshold for each node. So we're just going to simplify the model and then just iterate the nodes. So maybe n in the nodes of the graph, and say config.add node configuration. So you add properties to the node, say threshold I threshold. Okay, and then just say Alright, so then just say what model.set initial status configuration iterations equal model.iteration bunch 200. Let's say that the maximum iteration is 200 iteration. Now the tipping model was here. Let me find it. Here. Now the k here is basically determined by the theta and the number of the degree of the degree of the set of incoming neighbors of a certain node v sub I. Now we've specified the threshold as 0.15, so theta v sub I for each node here will be 0.15. Okay, now let me execute in interactive mode this time the tipping model as, not at, it's as. Okay, threshold model. Okay, so instead of writing import ndlib.models.epidemics.threshold model as tm, you should just import it from the epidemics. From the epidemics model, you import this module, and then just replace tm.threshold model with only threshold model. And I've changed the number of nodes from 1000 to 20 just for visualization purposes, and the iteration bunch at 10. Now let us re-execute it. Now let us print the iterations, and we get a dictionary with the different iterations and the statuses of each node. 0 means it's not infected, 1 means it's infected. So at the first iteration we have only 10%, so 10% of 20 is 2, so we should have 14 which is infected, and we should have 16 which is infected. So from the initial nodes, from the initial 20 nodes, only 14 and 16 are infected. Now in iteration 1, 15 gets infected, so because maybe 14 and 15 or 16 and 15 were attached to it. And in the second iteration 13 is infected. In the fourth iteration, 3 is infected. In the fourth iteration nobody is infected. In the fifth iteration nobody is infected, and in the sixth no one, and so on and so forth. So basically when you reach a conversion state, because here if we didn't specify 10 as a maximum as the iteration number, the algorithm would have stopped at iteration 5. Here iteration 6, because we start from 0, so at iteration 6. So here, because the status, so the node and the activation function result doesn't change from the previous iteration here 4, which status is also empty. Now this is the tipping model. Now what we're going to do is we are going to view the independent cascade model. Now the independent cascade model is quite similar, the structure of the program is quite similar to the tipping model, which let me save it. So IC model.py, we import the network X as an X, and an X, and import ndlib.models.modelconfig as MC. Okay, and from ndlib.models.epidemics import independent cascades model. Okay, let me double check the spelling. Yeah, right. Okay, now we say we want to create an Erdos-Renyi graph again with 20 nodes. Let's say now we have 20% of probability for each node to get connected with one another. Let us independent cascade. Let us define the model. So let us give it the graph, the error-friendly graph. Let's define the model configuration. Okay, let us add the number of model parameter, the number of initially infected nodes. So percentage infected, say 0.1. So only 2 nodes will be infected at the beginning. And let us say that the transmission, which means that the transmission is the rate. Let us just be loyal to the theoretical notation, which is the probability of each node to transmit, right? So the probability of each node to infect its outgoing neighborhood. So yeah, we say here that the transmission is 0.6 for each node. So you can also specify different transition for different beta, so different beta probabilities for each node. I'm just going to choose one for simplicity. Iterate through the nodes in g.nodes, and then config.add node .add edge, configuration, and this is in edges because we need probabilities of edges, not of nodes. And this is inconveniently called, I don't know why, as a threshold. It shouldn't be called as a threshold, it should be transmission, transmission. But yeah, it's a strange design choice to call threshold something that is not a threshold. But yeah, nevertheless, you specify it like that. Initial status, config, and let us see iterations, model iterations, iteration bunch, 20 iterations. Now let's say 10. Okay. Execute in interactive mode. What's its name? IC model. Has no attribute model config. Sorry. No, configuration. Okay. Yeah, that's my bad. Okay, so now it should be, add model parameter. Okay, so we have that. We print the iterations and we see that a status of 1 means that the node is infected. A status of 0 means that the node is not infected, so it's not active. Here we should have 2 ones, so node 15 and node 7 initially are infected. Let us see. In the first iteration we have 7, which gets removed because here we have 3 different states, but in fact there are only 2. But in the next iteration, basically the nodes that have already been infected in the previous iteration don't then play a role to infect new nodes, right? So they infect new nodes, right? So for example, I have node 1 which has been infected in iteration 0, and then in iteration 1 node 1 infects let's say 2, 3 and 4. Okay, so 2, 3 and 4 would have the code 1, so infected, whereas node 1 would have a code 2 in order to distinguish it in the third iteration and say, okay, node 1, you cannot infect any more other nodes. You are infected, but you are not going to infect other nodes. So imagine as if node 1 would be put in a quarantine and it would be still infected, but it wouldn't be able to infect other nodes, whereas the other nodes that have been infected by 1 go freely to infect other nodes until they get quarantined in the next iteration. So code 2 is to represent this kind of phenomenon. But yeah, we see that because of the transmission probability, which is 0.6, we get these nodes which are infected, so 10, 11, 14 and 19 and so on and so forth. So this is the This is quite simple because they follow the same structure, because they belong to the same library. It's very useful to follow the same structure. And notice that you can specify different transmission for different edges, so this probability here can change with each edge. Now let us move to the final model, which is the linear threshold model, but we are going to implement this on our own. Let us say LT model. Now maybe capital letters, LT model.py. Okay, so here we are going to import the network X as an X, and import random, import copy. Now let's say that we define a function linear threshold, and we give it a G, which is a graph, and how to say, an initially active node S, initially set of active nodes. Okay, now for n, we want to generate a random threshold for each node, right? So for n in nx nodes, g dot node n threshold, okay, is random dot random. This generates a random number from 0 to 1. And let's say wave, so t is equal to 0, or maybe wave, yeah, wave is more explanatory. Diffusion will contain is a directory which contains the infected nodes in each wave or in each iteration. So in each iteration I'm going to say which nodes have been infected. Okay, now diffusion 0, which is the beginning of the algorithm, I'm going to copy, so deep copy, because I don't want to modify S. I want to deep copy the content of the of S, not the content, but the content of S. Okay, so active nodes right now, because we haven't done any iteration, the active nodes are the initially active nodes in this set S. Okay, so while true, so until I find a convergence condition, I am going to say, okay, which are the nodes? So this is a list that contains the nodes which have been added in the current iteration. Okay, and we increment the wave by 1, so we move to the next iteration, and then do it for each node. For each node, if that node is not inactive, so if that node is inactive, check its incoming edges, so incoming neighbors, right? Now remember that we have to check the incoming neighbors here because we need to sum their weights, so their probability, and see whether the sum of those probability exceeds the threshold of node n here. So n data equal true, so data equal true will give me the edges, so will give me the incoming and outcoming, so the two extremities of an edge E, which will be one extremity will be n and the other extremity will be the incoming node, so the incoming part of the edge. Okay, if edge 0 inactive, so if this the node corresponding to the incoming node, so the node the incoming node is already active, we need to I need to say influence equals 0, so influence will be sum of weights, some weights, right? Some weights will tell me the sum of the probabilities, so of the weights, right? float edge 2 weight, and okay, so this is 1 if, okay, so that's it. So now if influence g if some weights is greater than or equal to the threshold, so n threshold, then I need to append this node to the active set, and I need to tell added.append, and so I need to say, okay, this is the we add the a node and tell that we have something, we have influenced something, because if we don't have something influenced, then we have the criteria of convergence. So this is why this list is necessary. Now, okay, if len added, right, is equal to 0, then break. So it means that we go out of this for loop and we have finished the spreading of influence algorithm. Else, the diffusion of the waves, so the dictionary that contains the history of what has been influenced throughout the different waves, should be equal to the set of added, right? And we return diffusion. Okay, so how are we going to so how do we now add the how do we create the graph, and how do we use this function? Basically, I went off screen and created the graph with this structure, so the edges follow this graph structure, and I assigned the weight at random for each graph. Now you have also the thresholds that are going to be assigned at random, so they will follow a probabilistic distribution, but we are violating this constraint, where the constraint that I said that the sum of the weights of the incoming edges should be lower than or equal to 1. Lower than or equal to 1. Here we do not satisfy that constraint, but it's fine. If you want to be more correct, then basically you can also satisfy that constraint. I didn't bother to satisfy that constraint because I am just wanting to show you how the procedure works. So I created a direct graph, so this DI prefix for the graph stands for directed, and the initial infected nodes are the 1 and 2 node, and then I call the linear threshold function here, which returns me with a dictionary of where the keys are the iterations, so the waves, and the values are the added nodes. Okay, we can also execute it. Okay, no, wait, execute it. Why does it print? Okay, let me see. Why does it print? So, okay, diffusion, fusion. So we have these. So we converged immediately. Now let us see with another try. Yeah, now we have two different iterations. So the first iteration is the one with the initial infected nodes, and the second iteration, so iteration 1 here, is the iteration which consists of other nodes such as the node 4 and node 7, which have been infected in the second iteration. So yeah, this is the linear threshold implemented by us. We haven't used any pre-built libraries except network X, the built-in functions such as random and copy. You can also use NumPy to generate random numbers. But yeah, this is the whole the most basic spreading of influence models that there are in the literature, and we have finished right now. So the linear threshold model is not that difficult. You just need to take care of some indices in the graph. It might be a bit weird that you have to access the nodes and then access the node with a certain index and then the threshold or the weight for an edge and so on and so forth. So yeah, so this is what we did this week, and I hope that you enjoyed it.